Okay, I want to do a quick video on, well, it might not be that quick because this takes a little while to explain, but a video on explaining tooling and setting of tools and doing various things on this machine, because I've had quite a few questions about that, and there must be people that are using this control or this similar type machine and they want to know about this. Might not be so much a video for the general audience because it's going to be more kind of technical in nature on the various things on machining and setting of tool offsets and things like that. But this machine, I'll answer this question because I've had this question to begin with, is a Mazak Integrex E650H machine. So this is classified as what you might call a mill turn machine, where it does milling and turning all in the same operation. It's more of a milling machine than a turning machine, though. People get this kind of backwards, and a lot of people do a lot of turning on this machine without milling, this type of machine, I should say, and it's not really the most efficient thing to do with this kind of a machine. But anyway, the focus of this video is going to be more on tooling, you know, and how they mount in the spindle, and how you touch them off, and how you set various tools to do different kinds of operations. Now I've changed to this tool here, which is a, I don't know if you can see that very well. Let me jog it back here a little bit and over closer. Now this tool is a OD turning tool, is the way it's set up in the machine, although it can do a lot of different things. It just depends on how it's mounted and configured in the tool setup on the machine. In fact, let's talk about that to begin with. The Mazak Integrex type of machines, or there's other brands, you know, like Doosan, you know, Morsiki, whatever, but they all do basically the same thing. They orient the tool and clamp it for a turning tool, and of course a milling tool can rotate like on a milling machine. But the way these machines do that, or the way this machine does it in particular, excuse me, is it has a coupling in here, curved coupling they call it, which is a disc with teeth on it that are sort of like, almost like gear teeth, coarse gear teeth that stick out on both sides on this machine. And then they have two kind of, I don't know how you describe these, like ring-like hydraulic pistons that engage this coupling, or this disc, with the teeth on it that have mating teeth that engage it. So when it clamps that for a turning tool, it takes the force into that instead of the force being transmitted into the spindle bearings of the milling spindle. And this coupling this machine has what they call a flex tool option, which means that it can index and clamp the tool every 15 degrees of rotation of the spindle. Normally, you mostly clamp the tool in this orientation or the other for turning. And so they in the manual tool setup, if I go over here to the control and I push the machine button here, and I get this display, and I push spindle, and I can unclamp this tool. Right now the tool is oriented and clamped because this is enabled, the clamp thing. But if I disable that, now I can rotate the tool freely as if it was a milling tool. And this tool is set up to orient in what they call the 180 degree orientation, and then the other orientation for most turning tools is that orientation, the normal in this case. Normal and 180 is kind of a arbitrary term because you can set these tools up in various different ways. If you have a Sandvik, for instance, boring bar with a serrated mounting for the head, you can mount the head either direction, and so you could have it orient in either direction. So to turn the direction you want to turn, if you will. So that really doesn't matter, but what it does come into play is when you have it oriented in the normal orientation, when you take the tool in and out of the spindle, the capto taper has this little key and this hole in it, and on this machine, when it's oriented normal, they call it, that always faces towards the back of the machine, so you know how to put the tool in the spindle like that and clamp it with the drawbar, which I can do manually on this page, if you will, of the control. I can manually clamp and unclamp it by selecting these keys. This is a manual operation. Normally you don't do any of this when you're running the machine. I'm just doing it manually right now. So that direction is the normal orientation of this tool, and then I would clamp it here. So that coupling in here, and now it's solidly mounted. So it can't rotate, and the force is directed through that coupling into the spindle head, not through the bearings or anything like that of the milling spindle. Now, I don't know how they did this, but there's two like ring cylinders, hydraulic cylinders that clamp onto this curvic coupling disc, if you will, in here. And however they've made that, I don't know how they did it, but it does not move the spindle. It doesn't shift it in any direction when it clamps and unclamps, or it's so small you don't really have to worry about it. I'm not sure how they achieve that precision, but it's really quite precise, and it doesn't shift this. You might think, well, if they're just clamping into the spindle, it would shift the spindle back and forth, with the preload of the bearings would give, but it doesn't do that. Somehow they've made it work that way. I'm not sure how they did that, but it does work really nicely like that. So now this tool is clamped in a turning setup. But if we go to let me see, there's a lot of things to explain here as I'm trying to figure out how to do this. We go to the tool setup, and I'm going to scroll down to that tool, which is the highlighted tool here. I'm going to cursor over so I transfer over to this side of the screen. If you can, I don't know if you can see that in the video, but this little purple frame around the box on the display moves back and forth if you select this toggle button down here. And you'll notice that this tool, a turning tool, has what they call an A and a B dimension. The A dimension is the length from the gauge face of the spindle up to the end of the tool, and the B dimension here, which is this entry over here, is from the center line of the spindle up, like this. So you would basically visualize, if you had this center line of this spindle up at the tip of this cutting edge, that you would move back and down to get to your A and B dimension. So in this direction, it's a positive number because you're moving in the positive Z direction, and in this direction, it's a negative number because you're coming from here with the center line down in the X direction, if that makes kind of sense. So that B dimension for a turning tool facing this way is negative, and the Z is always positive. It's the length of the tool. And that's very similar to a milling tool too. The milling tool is on center line, so there's no well, let me find a milling tool. Like here's an end mill, and there's no A and B on the offset of a milling tool. It's just this is a milling tool. They show a lathe tool in the same picture, and it's only the length that matters on a milling tool. So if you have those dimensions, those are pretty easy to achieve by touching the tool off. Then you have to, of course, have the orientation correct. And this particular tool is in what they call the reverse orientation, and clamped there. And on a lathe setup, this always clamps the spindle, the milling spindle, with the coupling on this setup for a lathe tool, or a turning tool, they call it. On a milling tool, it does not. There is a function on the machine that if you have a, how do I explain this? If you have a milling tool in there that is not clamped, in other words, the spindle could freely rotate, it will not let you do a turning operation. It'll give an alarm if you have that tool in the spindle, but then you try to do a turning operation. It won't let you do it. Now, it'll kind of let you do the reverse of that, where you want to do a milling operation with a turning tool like this. Like in the past, I've used this as a fly cutter, as like a milling fly cutter, this exact tool, and it will let you do that, but it kind of doesn't let you do the reverse because it knows that it needs a tool to be clamped for turning. Now, there is some functions on these type of machines that will allow you to rotate both spindles at once, like a hobbing function or ability, and I forget what they call that other way of doing where you're using a fly cutter and you're making flats, and like a hex or a square or an octagon or whatever with a fly cutter, and it's synchronized to the spindle. I have to look that up. I'll put it on the video, a text or something, the name of it. But this machine doesn't have that option, but this machine does have the hobbing option, which means I could synchronize the milling spindle to the C-axis, really. It's more of the C-axis and the milling spindle rotating in synchronous, so you could mill a gear teeth if you had the proper tooling in the spindle, like a hob, and you tip the B-axis at a certain angle, and then you can synchronize that with the hobbing and mill gears and things like that. The other type where you're just using a fly cutter, I think it actually runs the turning spindle with that option, but this machine doesn't have that. So those are the kind of the ways that this works. And this over here at the control, this orientation on this machine, because it has the flex tool option, you can put an angle in here of every 15 degrees, and it'll rotate the tool to that angle that's specified here. But that's an option as well, and if you don't have that, you can only probably do, normal and reverse on this. I think this selection is standard, reverse, but see, I have what they call it. Well, they call it a flash tool here, and I can put an angle here if I select this key here. But I'm not going to do that on this tool, of course, because it's already set up this way. The tool above this, 6A. Also on tools on the Mazak, on the Integrex, well, on all Mazaks, really, they have these designations they call A, B, C, the letters of the alphabet. You can go all the way to Z, I think, but you can't really use certain ones because they're used in programs in certain ways, like I, J, and K, I think, or something. But all the other letters of the alphabet, you could have that same offset. Like you'll notice here, I got 1, 2, 3, 4, 5, 6, 7, 8, 9 offsets on this one tool right here. It goes all the way from A, B, C, D, E, F, G, and H, and J. Well, I guess they let you use J, but I think they don't want I. That's why I skipped H, I on that. But anyway, these are the letter designation is mostly for using the Mazatrol, and you give it priorities of which offset to use in the Mazatrol programming. So if you want to call this tool up like 6B in G code, you have to put tool 6.02. 01 is for A, 02 for B, 03 for C, and so on. You have to use a 0.01, 0.02, 0.03, 0.04, and so on down the alphabet to call a tool up like this in G code. And when you call the tool in G-code, or you do a tool change to this other tool, it'll automatically rotate and orient the spindle and clamp it for that setup that's defined in the tool setup page here, if that makes sense. So there's different kinds of turning tools for different ways of turning. Let me, if I was to jog this tool back and then index the B-axis over here, I'm just manually indexing it. That's as fast as it'll index with the doors open, by the way. Probably a safety feature, because that index is pretty fast when the doors are closed in the rapid mode. I'm going to bring this to Y0. I'm looking at this number right here. Just manually jogging it to Y0 for the time being, so I can describe something here. So this turning tool, the way this tool is defined, is normally used like this. Let me turn this light on so we can kind of get some more light here, because I want to talk about something here that happens. Now, you see, the reason I've made this smaller chuck like this and mounted it in the larger chuck is because of this interference problem on these kind of machines. See, if you're down here at small diameters, you're going to be hitting your chuck jaws on this if you're up close to the chuck. Like if I was going to face down the center with this tool, you could see if I was way up here with the part very shortly sticking out of this chuck, I'd be hitting the jaws because of the width or diameter of the spindle face here. And so I kind of get around that with using this smaller chuck, the way I do it. But there are different ways of clearing this on larger chucks. This is actually a smaller chuck than the machine came with. This is a about 16 and a half inch manual 4-jaw chuck. And the machine had a 21 inch Kitagawa hydraulically operated chuck on it when I got it. But for what I do, this is better because I get a bigger spindle bore taking the drawbar out. This is another question I get quite frequently asked. Why do I run a manual 4-jaw chuck on a CNC machine? But for the kind of machining I do, this is better because I don't do a lot of chucking and unchucking of parts, and so I can put it in the 4-jaw chuck and I can indicate it in very precisely, and it's not a big factor on the type of machine work I do as far as the time it takes to manually chuck the part with a manual 4-jaw. So that's the reason, one reason I use it. And also I do some kind of work that's a little bit off center sometimes, and like I said before, it gives me a bigger spindle bore because if I take the draw tube out of this machine, I have a 6 5/8 spindle bore that I can stick parts up into on this machine. So that's good. And also a manual 4-jaw chuck like this will hold the part more securely than a hydraulic chuck will. A hydraulically actuated chuck with spindle speed, and depending on what kind of top jaws you have on it, will reduce its chucking force as the speed increases due to centrifugal force on the jaws. And the part can actually come out of the chuck if you let it get going too fast. Now this machine will only turn 1600 RPM maximum in high range, so it's not that big of a problem, but on smaller CNC lathes where they turn 5, 6, 7,000 RPM, that can be a big issue with a hydraulic chuck, and you have to be aware of that. So in reality, when you have something chucked in a manual chuck like this and you tighten these jaws all down on it, there's no, well, I don't know, it would take a tremendous centrifugal force to open those jaws, and it just doesn't happen because the machine just can't really turn that fast in this case. So one thing I want to point out here is when you get, if you're up close to the chuck like this, with a turning tool like this, you see you only have a certain amount of space unless you make a real long tool, and then that becomes a problem with vibration and stuff. And so you can't really turn up close on this kind of machine with this type of tool unless the part's big in diameter. Like this chuck here is 8 inches in diameter, and so it can reach that and not hit the jaws. But if you're down to a small diameter part like this, like I showed earlier, you would be hitting your jaws on the part. So the B-axis on this machine can index and clamp itself kind of like the turning tool clamps in the spindle every 45 degrees. Like that. See, so it actually clamps itself in that angle. Now, this isn't the right kind of turning tool. What you would use is a turning tool like this in the spindle, up in here. And you can see, well, let me just, I'll tell you what, I have to have the B-axis horizontal to take the tool out of the spindle, this machine. I think it's some kind of maybe, I don't know, it's a safety thing they did. So I clamp that tool in there. So this would be kind of like the tool you would use if you were going to turn with a bigger chuck and you wanted to turn up to close to the chuck. You could get there because the chuck's jaws are not going to hit your spindle so much. If it's real close, you might put an extension on here, a short capto extension, and you could do it. So if you're doing, you can get right close up to that chuck, and the jaws are going to clear even if you did a facing cut all the way down the center line with that kind of a tool. Also, this kind of a tool can, as you can see, you could actually orient this tool. Let me select this back here, unclamp it, and orient it the other direction, and clamp it. You can actually turn right or left hand with this tool, because this insert's pretty much on center line, and you can rotate this tool back and forth, and you can also use it down vertical if you're profiling things and stuff like that. So these tools are kind of useful in that way. And it actually is shorter. If you see, it's shorter than this tool is, and it actually has more rigidity turning like this. Now the B-axis also has a curvic type coupling in its axis, and it clamps this very securely for the turning operations at these angles. So you could clamp it. If I index this, it'll index to V0 degrees. This is V0, and it clamps it. You probably can't hear that, but I can actually hear the coupling clamping. And then 45 down here. And 90. And 135. And 180. Like that. Now, if you had a machine with a turning spindle and the tail stock, you would be, of course, turning in these directions, and you could use that function. This machine will do it, but I don't have a turning tool over there, or turning spindle, I guess you'd say, and so I don't normally do this, but I can turn this direction like this, and I've done that before. The kind of little bit of a disadvantage of a tool like this, though, I don't know if you've noticed, but you trade one clearance for another clearance. So although you have more clearance here, you have less clearance on your tailstock, because your tailstock center would be here and the tailstock body, and you would be colliding with the machine here. So you have to kind of change back and forth tools in those cases between a standard turning tool, or more standard, I guess you might say, and one like this. I'm going to unclamp and reorient this the way it's supposed to be for this tool. So that's kind of like the 45-degree turning tool. that you can use on this type of machine to increase your clearance on the chuck jaws and things like that. So most of the milling that you do actually is at either on the face or on the OD, and it does clamp the B-axis very securely at those angles, and most of the time you use that when you're milling too as well. You can do that. Now I had a question from somebody about using a shaping tool in the spindle and how you can get it to do that. Let me. I think my tool 45. Let me go over here to the tool setup and look at tool 45. I think I had these tools defined. Yes. So 45.03. So let me change 45.03 input. This is the way you do kind of a manual tool change on this machine. And I have to close the doors here. You notice I have to push both of these switches, one on each side, to close these doors on this machine, because you can't really do anything with the doors open. You'll see when it changes to this tool, it's going to highlight this offset 45C, 45.03 here when it actually gets to it. Right there, you can see it's highlighted it. Let me open the doors now. To open the doors, I got to hold this down, the door unlock key, and push these two buttons simultaneously opens both doors. Let me jog this tool closer over here so we can see what's happening here. Now this is the tool that I used on the anvils to shape the hardy hole, a square hole. First I drilled and I milled it as close as I could, and then I shaped out the corner square with this exact tool right here. So you can define a shaping tool like this. Let me go down to this offset on the control. And it's basically calling it a lathe tool here. And it has to be, well, it doesn't have to be, but it's better to define it like this because it clamps it securely, orients it, clamps it, and it holds the angle very precise on clamping. And if you just use the spindle orient, there's some give to that depending on how solid the motor itself can just hold it. But with this, you've clamped in the coupling and everything, and it's very securely held at a very precise angle. So if we look at the offsets here, we're going to see this is at the standard rotation orientation, and this is at 90 degrees. So see, I've entered an angle in for this one, and that's the reverse, and the other one here is at 270 degrees because I was actually rotating this tool at 90 degrees and doing each corner of the square. All right, just to demonstrate this, I put the camera inside the machine and closed the doors because I can't really film this too good outside. But it came in at 43 or 45.03, I should say, tool number. So we're going to change to 45.04. If we do this, it should just change the tool. It's just an M6 45.04. We got a tool change of 45.05. I'm just doing this in MDI to demonstrate it here to you. And we're going to change to 45.06. So this is how you can rotate this tool all the way around, and then tool change of 45.03. back to the beginning. So that's how you can do that. In the case of what I was doing, I was rotating the tool and orienting it, clamping it in those 4 angles to do each one of the 4 corners of the square hole and the hardy hole in the anvil. All right, so I kind of demonstrated what I did with that tool. Now I had another question with this on a turning tool I used on when I made the chess pieces. Let me change to that. I wrote it down here. It's tool 2.03. So we're going to do a tool change at 2.03. That. In the auto mode, I got to close the doors again. Or this is actually the MDI mode. I want to talk a little bit about this tool as well. Then we're going to change to that. All right, here we go. I'm going to bring this tool over to center line. I'm looking at this number right here, the y-axis. Doing this manually. Of course, this all happens automatically when the tool's actually running in the program. Okay, 0. Now, let me get a light here so you can see a little bit better. Just put this light here. That might help a little, maybe. I'm going to jog this up here now. This tool I was turning and this is just a VDMT boring head mounted on a Sandvik. This is really kind of like a boring bar, but it can be used, like I said before, as a turning tool as anything on this type of machine. But if you were using this in a standard lathe, it would be more like an offset boring bar. And I've just mounted my boring bar head on it, a VDMT head, and oriented it so it's facing down. Now this has the same geometry as that bigger OD turning tool when it was facing the other direction, as you saw earlier. So in order to touch this tool off, I would touch my 0 off on the face of the part here, my Z0. So let me go to the tool data on this tool. You see that that would be the A dimension would be, from the gauge face of the spindle out to here. And then I would skim an OD and mic it and then set my B dimension here, which is the distance from the tip of that insert to the center line of the spindle here, which happens to be, in this case, a positive direction because, like I said earlier, if you imagine you brought the center line and the face of that spindle to the tip of this insert, you would go upward in X and positive in Z. So that's what these numbers are. This B is an X number and this A number is a Z number. So you touch the tool off like that. And the reason I was using this tool was because on the little chess pieces, some of these angles on the back sides of those diameters were, or faces, were steeper than this tool could go down. Now this has the same geometry as the OD turning tool as far as the way the insert is located here, but if I run this to 45 degrees, well first, before I do that, notice let's look at the position display. Well, I precisely got to jog it to Z0, which is here, which is this number right here, and it's on Y0. X is whatever diameter it turns. It's already been offset, so I'm not going to mess with that, but normally you would, like I said, you would skim a diameter, mic the diameter, and then you got to set whatever half that radius, or half that diameter, the radius, the center line, and it calculates that for you. The control kind of calculates it. You can say, you jog the tool straight back, but don't move it in X, and then it says, how far is it away from center line, and it calculates the number of the distance from center line plus this distance. It subtracts it off of there, so it gets the number you want for your offset. The control will calculate that for you. But anyway, what I want to show here is now it's sitting at Z0, and the Mazatrol at about X1 point, well, I'm in the milling mode right here, so it's a radius. So let's change to the turning mode, and now it's more like it should be. 2 point. Let me bring it right down as close as I can to the diameter. This should be around 2 inches. Okay, let's just say 2 inches 10 thousandths. Let me bring it right to 2 inches. I think that's 2 inch stock. So we'll just say 2 inches. So it's sitting at Z0 and 2 inches right now, and you can see it's kind of far away for this camera, but it's right on the corner of this face. And the reason I want to show that is on the Mazatrol. On the Mazatrol control, it always follows the tip of the tool. So if I were to jog this up now and index the B-axis down to 45, which is the way I was using this tool, and if I brought that tool back up to 2 inches in X, let me precisely do it here. I'm looking at this number again right here. Okay, that's pretty close. And then we bring it up to 0 in Z, which is right there. I don't know if you can see that, but it's now, what it's using is the imaginary point of, if you drew 2 lines at the radius of the insert, and that's where it's actually lining this offset up to. So it's just it's like the tip radius of the insert out, because that's where the sharp corner would be. But what I want to point out is how you notice that the offset values or the values on the display change as the tool is rotated in the B-axis on this machine. And this in fact on any Mazatrol does that. It always updates whatever tool is in this case the spindle, but it can be the turret on a turret lathe. It always updates the position of the position display to relate to that tool. So you don't have to go to MDI and call up the offset and do all that business with the on a Mazatrol. Let me jog this up, and you can kind of see, I don't know if I was using this to cut the back diameters or back faces on the chest pieces, because when it's indexed at 45, the boring bar actually has, with the 35-degree diamond tool like this, actually has clearance on the back faces. So then I could get up close to the chuck here, much closer, to do those turning operations than I could with the other tool facing backwards. And that's the reason I was using this kind of tool for that. So you can do various things with different tools. Like I said, this is actually a boring bar, and normally it would be oriented like this when you're using it in the horizontal direction. If I index the B back to the horizontal, And you'd be down here boring a hole with it, of course. But I was using it the other orientation to do the OD turning. So you can do that with this machine. You're not restricted to which way the tool turns or anything like that for tools on these machines, because you can index them and turn both directions, or index the B-axis and turn with various different angles and things with the same tool. On the previous video on the chess pieces, I was turning the OD with it in this relation on the queen piece, I think, and then I indexed to the 45 to turn the back turning angles. And I think I could have done that on the other pieces as well, but I just didn't do it for some reason. Also, this had a restriction on I think it was the king or one of the pieces, no, the knight maybe, of it. It would hit the part because this wasn't enough distance right here to turn the depth of the knight piece, I believe, if I remember right. It would hit the OD before it got down there. So anyway, I don't know if this is interesting or of use. I could go into more detail. There's a lot more detail here about particularly about tool data and offsets, and how this machine, on a turning tool in particular, how you can use the tip comp direction. Now the way that I do that is kind of different, because the Mazatrol, I should explain this, I guess. If you're turning straight in Mazatrol, it always uses tip comp for every tool, every direction it's turning. It's compensated all the way around the tool. That's why on a turning tool, you need to make these entries on the Mazatrol, like the angle of the insert and the angle it sets in the machine, and of course the tip radius of the tool, and various settings like this in your tool definition. It probably, I don't use Mazatrol a lot. There's guys here that are really good with it, and they do fantastic things, but I don't like it too much for this type of machine. Well, the turning part of Mazatrol is great and it works good, but the milling part I'm not real impressed with, or I just don't like it. Maybe they hear the guys that use it or do some neat stuff with it, but me, I'm not really that good with it, and as far as the milling part of it. But on the turning part, you do have to define all these features of the tool, or it's not going to be able to do it correctly. But for EIA type programming, or G code, Mazatrol calls it EIA, you don't have to have any of this definition. It doesn't make any difference. The only thing you really need is a tip radius, maybe, depending on what you're doing. If you're turning with tip compensation, you do need this, and you need to know the direction of compensation. Now, because of Mazatrol always turns with tip compensation, it doesn't care what the direction is. It compensates all around the tool, the way you've defined the direction of turning and the cutting angles and the angle the insert sets at and all this stuff. So it compensates everything. Grooving tools, turning tools, everything. And it does it all automatically. But for G code or EIA programs, you do need to have a direction of compensation for tip comp. And this is where, this took me a while to figure this out, but on the Mazatrol control on this machine, because it can run EIA programs or G code programs, it has these offsets, and you can either use these offsets or you can use the Mazatrol offsets. But the only thing I use these offsets for, because these are designed more for what would you say, EIA programs, and with EIA programs you do need to have the tip comp direction of the turning tool, and so for the first 9 offsets here, I put in 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's all I put in. because you need to be able to refer to this if you're turning in a G-code type of program, EIA G-code program. But there is no way, if I go back to the Mazak definition of a turning tool, there is no entry for that the way they do it, except down here. And they just have this little thing that says number, and you put in this number. But this would mean nothing if you didn't have that other offset having the direction on it. So I've taken the first 9 offsets, I do nothing else with them but apply this tip comp direction. So in this case, a general outside diameter turning tool, if you're turning just the OD of a part and you're using tip comp, it would be in the number 3 direction. Now, I'm not going to go into a lot of detail in this video on that because that wasn't the purpose of this video, but there is 9 different directions that tip comp can be applied to a turning tool. This is kind of different than a milling tool. You got cutter comp, and it's just the round diameter of the tool, and that's pretty much it on a milling tool, and it compensates for the diameter or radius of the tool, if you will. But on a turning tool, it doesn't work that way. There's 9 different tip comp directions that you apply it to. And that deserves a whole separate video on itself. If that's of interest to people, I might make a video on that if there seems to be interest in that, because that can be a little bit confusing if you don't understand how that works. I don't really use it a lot. It is entirely necessary to use it depending on what you're doing with your turning tools. Now, most CAM softwares can compensate for this tip radius variations on turning tools when you get them tipped at different angles or going up tapers or around radiuses and things like that. And I generally do that in the CAM software for the most part. But if you're wanting to do a very precise thing with a turning tool, you may need to use tip compensation. Or let me give an example of one thing. If you're doing a groove that has corner radiuses broken on the OD, say it's an OD groove, and you want to break the corners between the OD of the part and the beginning of the groove, you want to deburr it basically, or break the corners. And a lot of drawings have sometimes very small dimensions for those, like 3/1000ths radius or 5/1000ths radius corner break. And generally speaking, you have to adjust the tip radius of the tool on the grooving tool and get those corner breaks just right. Even in the Mazak, you have to do that. It automatically does it, but in EIA programming or G-code, you got this radius program, which is little 5/1000ths radius, say, and say your tip radius of your grooving insert isn't exactly what they specify, or you've offset it in some way to control your dimensions, and it's just not breaking that corner the way you want it, or maybe it's not touching it at all because it's such a small radius. So you can decrease the tip radius value in your offset page, and it'll cut more into the part on just the radius. The diameters will remain the same, but the radius will cut more because it thinks the tool has you got to go the other way around. You got to increase the radius, so it thinks the tool has a bigger radius, and it pushes the tool more into the part, if that makes sense. You have to increase the radius to cut more. It's kind of opposite of a milling tool where you decrease the diameter to cut more off when you're using cutter comp. But on a lathe tool with the radius, the tip radius itself, if you increase the radius, it pushes the tool more into the part because it thinks it's got a bigger radius on the tool. So there's things like that, and we could go into that in more detail, but that really deserves a whole separate program to itself. I just wanted to answer a few of these questions I got in comments with this program because, like I said in the beginning of the program, it's very difficult to describe these kind of things in a comment on a YouTube video and make it understandable. Also because people have to kind of understand my language, and they might communicate a little bit differently than I do as far as the terms that we're using. And so I got these questions, and I just want to make this video to answer some of them. So thanks for watching. If you want me to go into more detail, put it in the comments on what you're interested in, and I can go into much more detail on this. There's a lot to go into, and I was trying to make this video as short as possible if I could.